Welcome back to section 3 of chapter 7. This section is going to be dealing with volumes. I'm actually splitting this section into 3 different parts because I see there's 3 different types of volumes that we're looking at, and so I think it'll be a little bit easier to see them separately. The first part is about the volume over a curve. So in the last section, we found the area between the two curves. In this section, we're going to look at what if we have a shape coming above the curve where each cross section is a geometric figure that we can find the area of.
What that looks like. And so the first thing is we're going to have an area. It could be an area kind of like what we were looking at yesterday or last time, or it could be a shape. It could be a rectangle. It could be any area on the graph. It could be bounded by the axes, or it could not. It could just be like this. And just like last time, we are going to take these and we're going to divide it up. And so we take a whole bunch of slices of it. The idea that we're getting here is like if we have a stack of papers or a book, we can look at each paper individually. We can find the area of that sheet of paper. Technically, the sheet of paper is actually a prism. It has volume, but the depth of that paper is super, super tiny. It's just this little slice, so it makes this volume tiny. However, when you add together over 1,000 pieces, you get Les Mis, which is a super thick book. It has a volume to it. So that's kind of the idea of what we're doing. So with this area, we then have to be given a little bit of information about the volume on top of it. There's a couple different things that are really common for the volume. One of which is the cross sections perpendicular to the x-axis. So like these little lines would be cross sections. They're going to be squares. What does that look like? Looks kind of like this. So we have these lines that I was drawing, and then we just get squares. So each piece here is going to be a square. We're going to find the area of each of the squares times the width, that would be dx in this case, and we're going to integrate from over the interval. So in this case, we're going to have the volume. It's going to go from 0 to 4. So we go from 0 to 4 of the area of each square. An area of a square is base times height, or base squared. What's the length of this base? It's what we were looking at yesterday. It's the top minus the bottom. So we're going to have the top square root x minus the bottom 1/8 x squared because that's how we get the area of the square times the width of the square dx. Integrate this, we're going to get volume. Now here we could distribute. When you distribute the squared, remember this isn't square root of x squared minus 1/8 x squared. You actually have to distribute to get 3 terms. Don't be that guy. And if you're doing it by hand, I recommend that first. You don't want to integrate from here. Or you could plug this into your calculator or integrate by hand and then plug it into your calculator to check your work afterwards. When you do, you'll get that the volume here is 72/35. And so, again, just like last time, I'm leaving this in the warm-ups for you to verify that. Can you type it in? Can you do it by hand to find that it's 72/35? I did it by hand, otherwise I would have ended up with a decimal and an approximation. So that's one thing. We could have also, instead of going perpendicular to the x-axis, we could have done the same thing, only perpendicular to the y-axis, in which case these would be the side length for the squares. We're going to have to multiply by dy, and we use the y as our bounds. Let's do this one in blue instead. So if we have squares perpendicular to the y-axis, they're going to be going the other way from here, but the volume, we're going to be going from 0 to 2, and we have to solve for our y's. This one over here we can square to get x equals y squared. Down here we can multiply by 8 and then square root to get x equals the square root of 8y. And this one is now the top one because it's the one furthest from the axis. So we'll have the square root of 8y minus y squared. That's this, but we have squares, so we have to square that, dy. And again, we could distribute and do it by hand, or you throw it into a calculator. When you do, if you do it by hand, you'll get the volume equals 144 over 35. And you can check that. That's warm-up problem 2 to see if you can do that one. Again, I recommend trying it by hand and then check your answer with the calculator. And so this is with squares. We do have a couple other common shapes that we use on top. Squares, semicircles, triangles, rectangles. Those are the big shapes that we use because we can find the area of those without too much information. I mean, we could have all sorts of random shapes on top. We could have amorphous blobs on top, but we would have to have a lot more information for that. And so this is the basic thing that we do. So with squares, we saw it kind of looks like that. Each cross section is a square. And the area, if this, we'll just call this y, since here it actually starts at 0 and goes up to the value. So it could be y, but whatever that is, that's the top minus the bottom is y. The volume will be the integral from a to b. This would be a and b of y squared dx. And again, y is going to be just the top minus the bottom. So that's for squares. That's what we just saw. We take it and we square it. How about semicircles? That looks kind of like this, where each piece is a semicircle and it moves up. So again, if we think of this as y, we can find this. The area of a circle is pi r squared. So a semicircle is going to be 1/2 of that. Well, the radius isn't actually y, that's the diameter. It's going to be half of y. So we'll have 1/2 of pi times 1/2 y squared, integrate from a to b dx, and we can do it that way. And we could also have a triangle. Equilateral triangles is the one we're showing here, but it could be any triangle. Remember, triangle is 1/2 base times height. It would give you information about the height. It could say it's an isosceles right triangle where the base, like one leg is on the XY plane. That means that it's going to be like a square, except it'll be 1/2 of that. The height could be twice the base, in which case we would just have to multiply by 2. But whatever it is we're doing, we're probably going to have a y times a y, or the top minus the bottom times the top minus the bottom, somewhere in there. There just might be other things. Same thing with rectangles. It could be a rectangle where it's twice as tall as it is wide. Same as a square, except we have two of them. So with equilateral triangles, we have the base, it's 1/2. The base we'll call y again. Just make that y. Again, that's top minus bottom. And then the height. The height for an equilateral triangle, which we could actually find, it's 60 degrees up there. We know that the height, if this is y, then that is root 3 over 2y because of trig. So if you use your special right triangles, SOHCAHTOA stuff, that's the height of an equilateral triangle. So we have 1/2 times y times root 3 over 2y. We're going to integrate from a to b, wherever a and b happen to be, times dx. Here we could move things around. We can multiply the root 3 over 2 and the 1/2. We could actually bring those outside of the integral too. So this could be root 3 over 4 times the integral from a to b of y squared dx. Just like over here in the semicircle, the 1/2 squared is 1/4 times 1/2 is 1/8. Pi is a variable. This could be pi over 8 times the integral of a to b of y squared dx. So a semicircle is pi over 8 of the squares. Equilateral triangles is root 3 over 4 of the squares. And so they can actually all tie back to the squares if you simplify it. Just with the way this type of problem works, that happens. So again, it's very similar to what we're doing in the last section, except now we're looking up above the graph and dealing with shapes up there as well. The process is the same. The stuff that you would have to show, even if you're doing it on your calculator, is the same. Just like what I was doing. You set it up, and then your volume equals your answer. How did you get there? Magic happened. Well, probably calculator happened. But you do need to set up the problem every time, even if you're using your calculator. Anyway, with that, see you in class. But till then, keep working problems, keep asking questions, and as always, happy mathing.